Okay, so I'm just going to move around the schematic here, and we'll look at where some of these components are and more on the G976 schematic. So this schematic is only of the implement hydraulic system. It does not show hydrostatic drive, although they're sharing a tank, so I guess technically it shows a little bit of the hydrostatic drive system. But if you want information about the all-wheel drive hydrostatic system and these hydrostatic pumps, then you've got to go to a different section in the manual. So I'm just going to start off here going around this schematic. And I suppose a good place to start would be the main implement pump. So right here, on the schematic, we've got our main implement pump. So there you can see we've got a pump with a variable arrow through it. And it's got a couple of pistons, it looks like, connected to the swash plate. This guy is our bias piston and spring, trying to push the swash plate to maximum angle. This is our control piston or D-stroke piston, trying to push the swash plate to minimum angle. So that's how they represent that schematically. The control that's on there has a pressure limiting compensator in it and a load sense regulator in it. And then you can see the springs are adjustable in those two. And then I also see a solenoid on the load sense control, because there is an unloading solenoid on this system. For cold startup, can you imagine the load that this starter motor is on, trying to crank over this, so there's our starter, trying to crank over this big Volvo D9 engine, plus trying to roll the input to the transmission, plus trying to roll over the hydrostatic drive pumps, transmission charge pump, fan pump, plus a very large implement pump. So to just give the engine a bit of a hand there and give the starter a bit of a hand, there is a solenoid that gets powered up, and it's on the pumps, and it's very hard to see when it's installed, but I'll show you that solenoid on the pump control, because I've got one off a machine, and it's wired up to the crank terminal of the starter. So when we're cranking the engine and the starter's rolling the engine, it's also powering up a solenoid. And what that solenoid does is physically kick the spool, the load sensing spool in the pump, over to help give a shot of oil to the control piston that's going to de-stroke and flatten that swash plate. So rather than having to build up some pressure to standby pressure during engine cranking, on this machine, they'll physically or electromechanically kick the spool over and kick oil into that D-stroke piston sooner, just to give the engine a little bit of a hand in starting. Some other interesting things on this pump. We can follow the suction line in from the tank. We can see there's also a check valve here, and we'll get to that in a second, but I also see there's a case drain line coming out of the pump. Looks like there's a case drain running back to the tank. So Volvo did not use ISO symbols here for this tank. I'm not sure what this sort of line is about, but this represents the tank on the schematic, and it's right across the bottom. So remember, piston pumps need a case drain. So that's the case drain line going out. It's unfiltered. It just heads right back to the tank on this machine. If something restricts the case drain, that's where this check valve can come in, and excess case pressure, instead of blowing the lip seal out of the pump, can actually push a check valve and a spring open that's in the head of the pump and push back into the suction. So if for some reason the case drain gets kinked, or more likely the pump manufacturer was expecting that the manufacturer or the machine manufacturer might put a case drain filter on here, and if the case drain filter were to get plugged, then they've got sort of a remedy for excess case pressure in the form of a check valve with a fairly substantial spring. But in the head of the pump, you can just take a screwdriver or something and push that open just to test that the spring is working. Coming off of the pump, looks like there's a pressure tap somewhere in there. I haven't actually seen it on this prototype machine, but somewhere you could hook up a test gauge. And then the line leaves, and I expect that's going to go to the priority valve down underneath the machine, and there it is. So it comes into the priority valve. Remember CF and EF on the priority valve. So pump flow comes into the priority valve. That's down underneath the engine on that bracket. So it comes into the priority valve at P. Lost my position here. Got the priority valve at P, and it will start off going to CF, control flow, which is going to head to the steering valve. So that runs up front, comes in. Here's our hydraulic steering valve. So C is the steering control valve. So C on the schematic is steering control valve at the front of the machine here. So it says Eaton on it. So it's an Eaton supplied valve. Again, same one essentially that's in the 310SG. Most manufacturers are now using that valve for anything that's got hydraulic steering and a steering wheel. So everything over here is steering. And there's the lines going way up front and crisscrossing to the two steering cylinders, the way we saw them welded in at the head ends of the cylinders to crisscross over to each other's rod ends. So we get the push-pull for the steering. So that's the actual steerable wheels to the tie rod ends to steer them. In that valve, we've got some port release and anti-cavitation check valves. And there's a Rotary unit in there. When we get to hydraulic steering, we'll see that. And then this mess is the rotary spool. It's a tough thing to reflect schematically, but that's it. Out of the EF port on the priority valve, I'd expect we're going to go to the 10-bank valve because that's everything else. If steering isn't taking the oil, then we'll let it go out EF, and it comes in, and here's the supply to the 10-bank valve. The 10-bank valve is huge on this schematic. It takes up about 1/3 of the page. Everything in here is part of that 10-bank valve. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spools, 10 sections. And you can see it is a sectional valve. They've got the dividing lines between the sections. And then all the lines run out of the work ports to the various hydraulic functions, mold board, lift, and side shift, and etc. Side shift is this cylinder. And the tilt cylinders for the mold board are here. So they're running out of, they've got their individual valve sections. So the side shift runs off of this control valve spool. The mold board tilt runs off of this spool valve. And they both, those functions run through this box. It's just an enclosure outline, looks like a manifold, and they put R on it. Well, that is our rotary coupling, or sometimes called a swivel. I'm just going to put the word swivel because that's less writing. And I guess they couldn't think of a good hydraulic symbol. I don't think there is an ISO symbol for a swivel or a rotary coupling, so they just drew it as a box. So let's go look and see where that lives on the machine. So that is here underneath this sort of trapezoidal shaped plate, and that's sort of dead circle, a dead center of where the circle would rotate around. So we've got oil lines traveling in, we've got oil lines coming in and out down here. Actually under that plate is where they connect on the top, and then they come down through and feed out to those two functions. So again, we've got our side shift cylinder down here, and we've got our tilt cylinders down here. So those two functions have to pass through a swivel because this circle rotates. And if you just connected it with hoses and you started rotating the circle, well, then you're going to rip the hoses off eventually. You're going to run out of hose as you keep rotating it. Or you'd have to stop and come back. Well, Volvo wanted to make this so it could continually rotate 360 degrees. You can pick the blade up to the side, and if you unpin the saddle, and you can have the circle continuously rotate. And that's because they're fed through that rotary coupling or swivel. And this is sort of the simplest analogy I can find for that swivel. We've got air pressure fed through to this hose reel that's rotating in the shop, and it comes in, and throughout 360 degrees of rotation of the hose reel, we continue to feed from the blue hose to the red hose. So this is a swivel in its simplest form. It allows something to rotate while continuously being fed under pressure. So this one's air, and this one's a little simpler because it's only got one connection on the circle. or underneath the circle of the grater, we've got 2 hydraulic functions, and they're double acting, so there's going to have to be at least 4 passages going through the swivel or the rotary coupling. So there's our 4 lines. So we've got a line going through that rotary coupling to the rod end of the side shift, to the head end of the side shift, and then teeing off to the rod end of the 2 tilt cylinders, and another one traveling through and teeing off and going to the head end of the 2 tilt cylinders. And then the swivel allows 360-degree rotation of these functions and continuously fed from these 4 lines. So that's what a swivel or rotary coupling does in hydraulics. It's not the most common place you're going to find one. The most common place you're going to find a swivel is in the center of every excavator. And then I also want to focus on S here. S here is the circle turn valve, which also I call more generically a rotary distributor. So we've got 2 cylinders here that are just double acting linear actuators, and they are fed from this section of the valve, and the work ports come out here and here, and they run up here and here through this circle turn valve, and that then sends the oil sequentially to rod and head end of these 2 cylinders to push and pull and turn the circle. So we're going to use 2 linear actuators to rotate something around. So these 2 cylinders that are fed from that rotary distributor or circle turn valve, which is here, those 2 cylinders sit here and here, and they're just linear actuators. So we need one to push and one to pull, and then this one needs to start pulling and this one needs to start pushing, and we need to get this action where they're sequentially pushing and pulling to rotate the circle. The other option Volvo had would be to put a hydraulic motor here with a gear that could drive externally on this gear of the circle, but they didn't. They put these 2 bell cranks and 2 gears that mesh off the bottom of each bell crank. There's covers there so we can't see them all that well, but there's a gear there driving the circle. And they do it in 2 places just so they're not going to break a tooth if they hit something. They're just sort of spreading the forces 2 places on the circle. So these need to rotate, and of course they need to push and pull, and you might think of it like your feet on the pedals of a bicycle. Now when your feet are on pedals of a bicycle, your brain works to tell you when to push one down and then push the other down, and when you're pushing down on one and it gets to the top and the other one gets to the bottom, your brain kind of says push 1 foot forward and pull 1 foot back and then start pushing down with the other foot. And there's a whole sequence of events that you're computing between your brain and your appendages to make that happen. Here, these cylinders aren't like your feet on bicycle pedals. They can't push or pull forward and back like your feet can as they go over center. So these 2 are actually offset a little bit, and there's a whole timing procedure between these 2 bell cranks and the gear in the center. So the gear in the center is actually following up. So the one gear is driving the circle here, one gear is driving the circle over here, and then this is a follow-up gear that drives the circle turn valve or the sequencing valve. And it's almost like a distributor on an ignition system of a gasoline engine, or an older one where the distributor is rotating and distributing the sparks to the spark plugs. This one's rotating and distributing oil to the proper sequence in these 4 hoses going to the head and rod ends of the cylinder so they can push and pull. And then they're out of phase. You can see this one's about the 10 o'clock position. This one's about the 2 o'clock position. They aren't half a turn away from each other like you might expect, because one's got to be able to pull the other one over center. So the torque on this circle isn't exactly even. It kind of comes in shifts as one pulls, one pushes, one pulls, one pushes, but they help each other to get over center. But those cylinders, as they extend and retract, move these bell cranks around and around. And then this valve sequences the oil. There's a spool in here that's being turned by that gear in the center, and then that spool sequences the oil that's coming from the valve, from the DCVs coming in these lines. And if we're going clockwise on the circle, then it sequences us head and rod properly to the cylinders. And if we're going counterclockwise and we're feeding oil from the other hose, it does the same thing in the opposite direction. So that is the circle turn valve, which is more generally a sequencing valve. So this is what that rotary coupling or swivel looks like. That goes down to the moldboard functions, the side shift, and the tilt. So this has nothing to do with circle turn, but it's because the circle turns, and we've got implements mounted down below it, that we need something like this. So this mounts to the gooseneck of the machine, and then as the circle turns, it moves this manifold part. This rotates inside here, this stem, and your hoses here are continually connected to the hoses here. So throughout 360 degrees of rotation of this piece, I don't know who the partners are, but whatever port, you know, this might be lined up with this might be lined up with this throughout 360 degrees of rotation. So oil pressure here will be continuously fed to here throughout the 360 degree rotation of that stem. We will focus on these a little more when we get into excavators. The circle turn valve that does that sequencing, got one off a slightly different grader. It looks like this. That third gear in between the two gears that are turning the circle turns this rotary spool, and then it automatically, the spool in here that turns automatically sequences the oil from the supply to the ports around here to push and pull the cylinder in sequence. So just this got the cap off it, but there's a snap ring that holds the spool in. So again, this one is for circle turn. It's a rotary distributor. It's much like an ignition distributor that might distribute sparks. It's got to be timed properly, and if it is timed properly, then as it rotates, it will sequence out the oil. Just going to continue across here, see if there's anything else that we specifically need to look at. Just more implement functions for, again, articulated steering, lifting of the circle, lifting of the angling the mold board. We've got our wheel lean function, etc. But the key ones I want to look at are the ones that pass through these unique components. The swivel for side shift and tilt, and then the circle turn valve or rotary distributor for the circle turn cylinders. At either end here on these functions, these are the lift cylinders for the circle, and you'll see some solenoids and solenoid operated valves with accumulators on them. That's an optional protection system that an operator can turn on, especially if they're traveling at high speed and doing grading. That way, if the mold board hits something, it provides some cushion to the cylinder so it don't blow a hose or damage something. This machine's not equipped with those, so I can't show you those on the machine. I'm told it was never a very popular option, but that's it. Going back to the priority valve for a second here. Again, coming off of EF, that's where our line came up and fed the supply to the 10-bank valve. So everybody in this 10-bank valve at the front of the cab gets their oil from the EF portion, which means they're not going to get a whole lot of oil until steering is satisfied. So steering gets the control flow to the steering. It's a very small system flow-wise compared to the rest of the machine, but it gets priority. Once it's happy, then everybody else can have oil from the pump. So that's off the priority valve. But the other place the EF port goes is to, I don't know why they drew it like this, they made it cross itself, but it comes up here, and at the supply of the main valve, they're showing it feeding a valve F, which is a 2-bank auxiliary valve option, which again this machine doesn't have. And it also feeds into G. They show an optional connection here. Yeah, off of EF it feeds into G as well. Not sure why they drew it like that one, but the G then is a 3-bank auxiliary valve. So we've got, if 10 banks aren't enough and you want to put more functionality on the machine, there's an optional 2-bank valve and an optional 3-bank valve, and you could run, you know, a snow wing or a V-plow on the front or a scarifier on the back of the machine. However, that console helm up there with all those control levers is pretty busy. So these extra valves, if you get auxiliary valves, then the stems get extended, and there's electric control paddles that go on there. They're not mechanically operated valves. They're electro-hydraulically actuated valves. Same Husco series as are 10-bank valve, but these ones are electrically actuated. So you see there's solenoid symbols. And on this schematic, they didn't show any detail. If they did, internally they would look just like these valves. Same series, but now instead of mechanically controlled, they're electrohydraulically controlled. So optional options for more valving. I'm not really sure what order makes the most sense here, but I'll jump down to H. H is kind of interesting. Well, H is actually part of A, but A is the supplemental steering system. It's a pump for it. So that is this guy. Again, aluminum gear pump down here, mounted on an electric motor. So aluminum gear pump. And that aluminum gear pump, the discharge line is here, and it comes out through a check valve. And then this line runs down underneath the engine to the CF port of the priority valve. So that line comes out through a check valve, I just pointed out, comes across here, and well, this connection right here is actually down at the priority valve, and then it connects to the hose that goes up to feed the steering. And there's another check valve at the priority valve. So when oil is normally coming out of CF, it comes out this way through this check valve and feeds the steering. If there's an emergency and the supplemental steering system kicks in, then it comes out through this check valve at H and feeds the steering valve this way. They need those two check valves so these systems don't try to cross feed each other. When this regular pump is working and oil's being fed to the steering from CF, we don't want it back feeding this gear pump down in here and trying to spin it like a hydraulic motor. If the steering system's working normally, there'll be pressure in this hose from whatever pressure's at the CF port of the priority valve. So we don't want it coming in here and trying to spin the gears backwards inside this valve. So there has to be a check valve there. So that's why there's a check valve. And then if there's an emergency and the supplemental pump kicks in, then it needs to close that check valve so it doesn't just try and backfeed the emergency, because the emergency might have been that this hose fell off. So we don't want to start dumping all our supplemental pump out on the ground. So check valves, when you've got two sources in one destination, pretty common to see check valves. They could have used a shuttle valve, but they've used two independent check valves. So that is our supplemental steering pump on the schematic. It shows an electric motor as the prime mover. It's a fixed displacement pump. We saw it was an aluminum gear pump. It does have a little relief valve built into it. I can't really get my camera under there. Maybe I can. Got my finger on the tip of it. I can't get my head down to see if I'm showing you anything of value. But down underneath there is the relief valve. That's just built into that supplier's pump. And then the check valve, as we saw. And then there's a pressure switch. This is actually, I don't know why they show it inside the enclosure here, because it's actually down at port P on the priority valve. But it's just measuring to see if the pressure is good from the main pump supply. If there is good pressure coming from the main pump supply, well, then this switch and relay will keep this pump off. But if we detect a loss of pressure with this switch and the transmission is in either forward or reverse gears, then automatically this electric motor will be fired up by a relay and a big solenoid here, and that will automatically turn on the supplemental pump to start feeding the steering. Very easy to test that system. All you need to do in one of these graders is just turn the key on, put the transmission in gear, but don't start the engine. So we won't have oil coming from the main pump. That switch will detect that, and it'll fire up the supplemental pump. So because of the environment this machine is traveling in, your failure could be something as simple as just running out of fuel. And if you run out of fuel and the engine quits when you're rolling down the highway at 20 miles an hour, then your main pump obviously isn't going to be turning anymore. That pressure switch will detect that, fire up the supplemental pump electrically. You won't have much control of any implements, but you will have front wheel steering to hopefully get you safely off to the side of the road. So that's supplemental pump. So A is pointing to the pump group itself. H is actually talking about that check valve in the discharge. So H is the check valve here, which is right there on the outlet of the pump. Now let's start looking at some load sensing components, because again, we said this pump is load sensing and also has a pressure limiting compensator. With load sensing systems, we have to have that signal coming back from the load sensing valves to tell the pump what the pressure requirements are in the various hydraulic cylinders or in the system. So that's what port X here is all about. So that port X is where load sense signal comes in to the spring chamber of the load sense control. So often that X is actually embossed right into the casting of the control valve that's bolted to the pump. So that's our load sense signal coming in. Where it comes from, originally, from the 10-bank valve, it's got to be picked up in ports A and B, the work port connections on the valve, but it's done internally. And again, we're going to start seeing shuttle valves that resolve not only as we looked at in our other schematic in our textbook between head and rod end of the cylinder, but now that we've got 10 hydraulic functions, we don't just have to figure out if there's high pressure in rod or head of a particular function. We have to figure out which of these 10 functions has the highest pressure. And whoever's got the highest pressure, because the operator might be quite talented in working 2 or 3 or maybe even 4 things at once. And if they are, well, then there could be various pressures. We need the pump to receive the highest, so it can build a pressure higher than the highest requirement out in the system. So there's shuttle valves built into that 10-bank valve, and they're going to sort out who of the 10 functions has the highest work port pressure. Once that's all sorted out internally in the valve, then the very highest pressure is going to come out this LS port. And they're using a dashed line, coming off of the shuttle valves. Not sure why they've labeled it up here, because it's actually this line down here. But after the last check valve internally, this line brings our load sense signal out and tries to send it towards the pump. Now, because this schematic shows auxiliary valves that are also load sensing, they have load sense signals coming out too. So whoever's higher between these two, whoever's higher between these 3 has been resolved internally. And then they come out, and then all these different load sense signals have to do battle to make sure the pump gets the very highest pressure. So this schematic shows 3 different main shuttle valves, an SV1, an SV2, and SV3. Coming from the 10-bank, pressure is going to do battle here with load sense signal coming out of the 3-bank. Then whoever's higher between those comes out, does battle with the 2-bank. Whoever's the highest or the winner of those 2 pressures is going to come out and do battle here at SV1 between the highest work port signal now versus steering load sense. So steering is also load sense. So it's going to one side of SV1. Our implement pressure is going to be on the other side. Whoever's got the highest load sense pressure now of the entire system of the machine comes down and finally goes to the pump. So that's quite a logic network of shuttle valves, all trying to figure out who on the machine's working the hardest. And it's like a manager trying to figure out who in the organization's working the hardest. Whoever's working the hardest, they're going to report that to head office and say, here, pump, this is the very highest pressure in the whole system. And then the pump says, okay, what is that pressure? Let's say it's, for discussion purposes, it's 2,000 PSI. Well, then the pump will put out a few hundred PSI more than that. It'll put out 2,300 to everything. Even the functions that didn't have that high of a pressure, everything's going to get 2,300 PSI. If the highest pressure coming back, let's say it's from circle turn. Circle turn's really working hard. 2,000 PSI load in the circle turn cylinders, gets picked up internally of the valve, sent out, does battle with all the other functions, steering and the 2 auxiliary valves if equipped, and whoever's the highest eventually makes it to the pump. In this case, it'd be that circle turn. Now, this machine doesn't have the 2 auxiliary valves on it, so it's only got SV1. It's only got a shuttle valve, and it only has to do battle between steering and implement. It's mounted on the front side of the tank for no reason other than convenience. And we've got steering load sense signal coming in one side, and 10 bank load sense signal coming in the other side. And then the hose in the center there running straight down is going to run down into the regulator with the green cap, and that's where the load sense chamber is on the pump. It's going to tell the pump that highest pressure. And then you may have seen another hose teed in there with that line, and that's running to a load sense relief. So I just circled that guy. There's our load sense relief, set at 3050 psi. So when the load sense signal goes to the main pump, it also tees and goes to a load sense relief. For whatever reason, Volvo wants to limit the maximum signal pressure going to the pump, and if they've limited that to 3050 psi, and then the pump load sense control is set to give us another, let's say for discussion purposes, 300. If the spring in there is set to 300, then that is going to effectively limit the pump's maximum output pressure to 3350. I don't know why they particularly did that, because that's the job of the pressure limiting compensator anyways. If you set the pressure limiting compensator to 3350, this valve's now coming from the Department of Redundancy department at Volvo. And as soon as you go to do any testing on the pump controls, the first thing they tell you to do in the service manual is take that hose off, disconnect it, plug both sides, and effectively get this load sense signal relief out of the system. So I did that. The first couple of times I tested the machine, hooked it back up, then I tested again the next semester, and eventually I started questioning, why am I hooking this up? So now it's just been disconnected and we don't bother hooking it back up. But where that lives, that signal relief valve, another illogical spot, is right here. You can just see the, just put my pen on the adjustment cap. So that's where the load sense signal relief lives. This one, the hose is disconnected and it's no longer part of the hydraulic system. We've just completely plugged off that hose. So we're going to rely on our pressure limiting compensator to limit maximum system pressure. Let's keep going. Let's look at the fan pump. So there's another load sensing and pressure limiting compensated pump right here. Looks very similar to our main implement and steering pump that feeds the priority valve. This one though is much smaller, but still a load sensing pump, and it's feeding the hydraulic fan. So it's also a variable displacement piston pump. The actuator in it looks a little different. Remember I mentioned that I've seen some that only have a spring versus a D-stroke piston or a control piston. That's the type this is. It kind of makes the engine surge a little bit when it goes on and off of load. So a little simpler pump, but it still has a swash plate in there, still has a bias spring trying to push